So today we're going to cover chapter 6, section 2. Today we're going to learn about bisectors of triangles. So the first thing we need to do before we begin looking for these specific points of concurrency is define what concurrent lines are and what a point of concurrency is. So concurrent lines are just three or more lines, rays, segments that intersect at the same point. And that point of intersection is called the point of concurrency. So for example, if I were to draw a bunch of lines on my paper here, and then have them all intersect, all of these lines that I just drew, these are all concurrent lines, and the point where they all intersect is called the point of concurrency. So our first point of concurrency is called the circumcenter. And the circumcenter is the point of concurrency of the three perpendicular bisectors of a triangle. When you have the three perpendicular bisectors, if the triangle that you're drawing the perpendicular bisectors in is an acute triangle, then the circumcenter will be located inside the triangle. And that's that first picture at the bottom. The one in the middle is a picture of a right triangle, and the circumcenter of a right triangle is always located on the triangle. And then when it's an obtuse triangle, the circumcenter will be located outside of the triangle. This is going to be a chapter where I can bring in a lot of sometimes, always, or never questions. So you're going to need to find a way to memorize the location of these points of concurrency. So whether you come up with a letter acronym or a rhyme or whatever it may be. So for example, for the acute triangle, maybe you might want to think of this as being the letters AI. So AI, acute, inside. For the right triangle, it's always located on the triangle, so maybe think right on. And then for the obtuse triangle, it's always outside, so maybe think of that as OO. Whatever's going to help you to remember the location of this circumcenter. The other bullet point that was on here is a vocabulary term, and that term is circumscribed. So the circle with center P is said to be circumscribed about the triangle. So in other words, if you look at the picture, all of the circles are pictured outside of the triangle. So when we're trying to find this point of concurrency, this circumcenter, what we're going to be doing is finding the midpoint of the side of the triangle, and then we'll be drawing in the perpendicular bisector. And we'll be doing that for the three sides, and then find the point of intersection, which will be our circumcenter. The circumcenter theorem states that the circumcenter of a triangle is going to be equidistant from the vertices of the triangle. So in this picture, all of the perpendicular bisectors, they're all pictured in blue. So I could go ahead, just to clarify that these blue segments are perpendicular bisectors, add in the right angle, add in the congruency mark, because remember, the perpendicular bisector hits at the midpoint and splits that side into congruent pieces. So BE would be congruent to EC, and then AF would be congruent to FC. Points D, E, and F, these are all the midpoints of the sides of your triangle, because that's where your perpendicular bisector is going to hit. Now, all of the red lines, these are going to be the equidistant segments that go from this point of concurrency, this circumcenter P, to each of the vertices. So it goes from the center to the vertices, and all of the red lines are congruent because they're all equidistant from P to each vertice. And the vertices are A, B, and C, so I could draw a segment coming out of P to each vertice and all of these red lines are going to be congruent. Now, the perpendicular bisectors, the blue ones, they are not congruent. Only the segments coming out of the circumcenter to the vertices are the congruent segments. So here's an example of finding the circumcenter. So step number 1 is going to be to graph the triangle. So we're going to graph triangle ABC here. So the order pair for A is the order pair 0, 3. For B, 0, -1. And C, 6, -1. Anybody remember where the circumcenter is located when it's a right triangle? On the triangle, good. And the bottom line here, here's the big hint, it's always going to be located at the midpoint of the hypotenuse. So if you get a question on the test where it asks you to find the circumcenter of a right triangle, and you know which segment forms the hypotenuse, just find the midpoint of it. But I'm going to show you all of the steps that you would need to follow just in case it's an obtuse or an acute triangle. So the next thing what we need to do is find the equations for the two perpendicular bisectors, which was question number 9 last night. So we're going to find the equations for 2 of the perpendicular bisectors. The triangle actually has 3, but once we find that point of intersection of 2 of the perpendicular bisectors, the third one will have that same point of intersection. So we're going to find the equations for 2 of the perpendicular bisectors, and what we're going to be using is we're going to be using the slopes of perpendicular lines theorem, which basically states that once you find the slope of the line, we turn it to opposite reciprocal. And then we're also going to be finding the midpoint of the sides. So we're going to find midpoints. And that formula is x1 plus x2 divided by 2, y1 plus y2 divided by 2. So the first thing I'm going to do is I'm going to be working on finding the midpoint of AB. So the point for A was 0, 3. The point for B was the order pair 0, -1. So again, that midpoint formula, x1 plus x2 divided by 2. Add your y's, divide by 2. So let's plug it in. So 0 plus 0, divide by 2. 3 plus -1, divide by 2. 0 over 2, 2 over 2. So my midpoint is the order pair 0, 1. So this is the midpoint of AB, which is located right here. Now, remember, one thing also to remember is that vertical lines and horizontal lines together form perpendicular lines. So notice AB is a vertical line. So its perpendicular bisector is just going to be this horizontal line hitting at the midpoint. Because notice it's created this little piece congruent to this, and perpendicular lines are horizontal and vertical. Now, if this were not a right triangle, side AB of the triangle could be a diagonal line, and we would have had to have calculated the slope of AB and then turn it to opposite reciprocal, then find the equation in y equals mx plus b, using that reciprocal and opposite sign slope with the midpoint, like number 9 in the homework last night. However, AB has a slope that's undefined, and I know that with the horizontal line, which has a slope of 0, these are my 2 equations. So the equation of that line that I just drew in blue is the equation y equals 1. Next thing I'm going to do is find the equation for another perpendicular bisector. So this is the first one. I'm going to go ahead and find the perpendicular bisector for side BC. So for BC, those ordered pairs, 0, -1, 6, -1. I need to calculate the midpoint. 0 plus 6 divide by 2, -1 plus -1 divide by 2. I end up getting 6 over 2, -2 over 2. So my midpoint of BC is going to be the ordered pair 3, -1. So if I plot that and then now draw in the perpendicular segment that goes through that point, I can see it's just going to be the vertical line because horizontal and vertical lines are perpendicular. Notice again, it split the segment into two congruent pieces. I've now found their point of intersection. The point of intersection of these two perpendicular bisectors is the ordered pair 3, 1, which is your circumcenter. Now, if these were not horizontal and vertical lines, then you would have come up with the equations in slope-intercept form, and then you would have either had to use the method of substitution or elimination to find the point of intersection. Let me show you the midpoint of AC. So AC's midpoint, which is going to be our circumcenter, A is 0, 3. C is 6, -1. Add your x's, divide by 2. Add your y's, divide by 2. 6 over 2, 2 over 2, 3, 1. And that's your circumcenter. Next, we're going to talk about the incenter. And this is your point of concurrency of the three angle bisectors of the triangle. This one's easier. The incenter always lies inside the triangle. Doesn't matter if it's acute, obtuse, or right, it's always inside the triangle. And in this picture, the circle is said to be inscribed within the triangle. So in other words, think of the word inscribed as being inside. So the circle is inside the triangle. Now, in this particular picture, all of the red lines are the angle bisectors. And the way that I can tell that they're angle bisectors is because of the congruency mark at each vertice. Notice how each of these angles have been split into two congruent pieces. So the red is all the angle bisectors. And the point where all of those angle bisectors meet is called the incenter. So this point of concurrency where they all intersect is called the incenter, and notice it's inside the triangle. So the incenter theorem states that the incenter of a triangle will be equidistant from the sides of the triangle. So in this particular picture, notice all of the red lines. So again, the red are the angle bisectors. The blue lines are going to be the equidistant segments. So in this picture, PD is congruent to PE, which is congruent to PF. The point of concurrency where all of the red lines are meeting is called the incenter. And from that incenter, I can draw little segments going out to the sides that are all going to be the same length. And those are the equidistant segments. Now, these blue lines are not perpendicular bisectors. Notice they're not hitting right in the middle of the side of the sides. So those are just the equidistant segments. They're not perpendicular bisectors. And then again, the red are the angle bisectors. The angle bisectors are not congruent, but the blue segments are. All right, example 2. It says, in the figure shown, ND, so this little blue segment here, is a length of 5x minus 1. And E has a length of 2x plus 11. Notice all of the red lines in this picture. These are all my angle bisectors. And we can tell that they're angle bisectors because of the congruency marks at each of the vertices. They have split angle A, B, and C into 2 congruent pieces. So all of the red are the angle bisectors. All of the blue are the equidistant segments. So in this picture, I can see that NE is going to be congruent to ND, which is going to be congruent to NF. My point of concurrency, my in-center, is point N. That is where all my angle bisectors are meeting. So in order to find NF, which is equal to NE and ND, since they gave me NE and ND, I'm going to set those two expressions equal to each other. So to find NF, I'm going to do ND is equal to NE. ND is 5x minus 1. NE is 2x plus 11. Subtract 2. 3x minus 1 equals 11. Add 1. 3x equals 12. Divide by 3. And x equals 4. Now, it didn't ask for x. It wants the length of NF. So remember, ND equals NE, which equals NF. So it doesn't matter if I plug in 4 into ND, which is the 5x minus 1, or to NE, which is the 2x plus 11. So 5 times 4 minus 1, 20 minus 1, and I get 19. If I would have plugged it in to the NE, 2 times 4 plus 11, 8 plus 11, and I get 19 that way either way. So ND, NE, and F, they're all 19. So NF is 19. Now for the next one, it says, can NG be equal to 18? So let me zoom into the picture here. NG is right here. This little segment here. Remember, the perpendicular segment is always the shortest distance. Remember my alligator-infested river example? Here's the river. And remember, if I want to swim across this river, the shortest distance is the perpendicular segment. And I already know the length of this thing. It's 19. So there's no way a segment drawn this way, this NG, can be shorter than NF. So NG cannot equal 18 because this one is already the shortest. So NF or NG cannot equal 18 because NF is already the shortest distance. And that is it for the notes on example or note 6 for section 6.2. Now for the homework tonight, you're going to show work for numbers 4, 5, 6, and 7. For number 4, it's like example 1. And I want to see you graph. So put a picture of a coordinate plane in there and graph it. But remember, what you can do to confirm your answer is just find the midpoint of the hypotenuse.